Alright guys, so in this first video I just want to talk a little bit about capacitors, remind you what they are and how we use them, and how they're going to affect our circuits. Alright, so the first thing to remember is that the purpose of a capacitor is to store energy. Alright, so if I've got a normal everyday battery here and I connect it to a capacitor. Now, one of the things that you're going to want to be able to do is talk about what happens as the switch opens and closes. So we're going to have the switch open right now, okay, which means that no current's going to flow because we don't have a circuit there. But as soon as we close the circuit, as soon as that switch closes, then you have a positive here and a negative here, which means electrons are going to flow down to this side, and then electrons are going to flow from your capacitor over to this side, which means you're going to build up a positive on this side and a negative on that side. Now, essentially what you're doing is you're building up the amount of charge that's sitting on that capacitor. Now, remember, we defined it earlier in the year. We said that the potential difference across a capacitor is equal to the charge stored on that capacitor divided by the capacitance of the capacitor, just like that. Now, we also showed that the capacitance depended on essentially four things, okay? The dielectric constant, which was the K, and remember that that was dependent on whatever was in between your parallel plates. Okay, we also have this permittivity of free space, which is one of your constants, so I'm not going to write that down. You've got the area, so that's the surface area of your capacitors. Now remember, we're talking about parallel plate capacitors here, and so the two plates have the same surface area, and then D being the distance between them. Now remember, this means that for a given capacitor, the capacitance won't change. And so therefore, the amount of charge that it can hold depends on how much potential difference you apply to it. Now, in the original situation over here, when we applied the potential difference in the beginning, there was no potential difference across the capacitor. And so there was no charge stored. But as time progresses, as the charge builds up, then we start to get a potential difference across the capacitor here. Now, eventually, this potential difference will be the same as our battery here, okay? Now, there are a couple of things that this leads to. Number one, when the switch is initially closed, there is essentially zero resistance. It acts as if there is zero resistance there, and so the current just flows freely as fast as it possibly can, all right? Now, as it loads up, there starts to be a larger and larger potential difference across that capacitor, which means that there's less of a driving force. There's less of a difference, because remember, the driving force, as we decide what goes from here to here, is that potential difference. And initially, there is a potential difference, but as time progresses, there is less and less of a potential difference between the battery and the parallel plates, which means that the driving force is less. And so there tends to be less and less current. Effectively, there's more and more resistance. Now, there isn't actually a resistor there, but effectively, the current's going to change because of the fact that the capacitor is building up with charge. Now, as the capacitor gets to the point where its potential difference is the same as that of the battery or the cell, now we're at the point where no more current will flow. In other words, when the potential difference of our cell is equal to the potential difference of the capacitor, no more current will flow. Now, this should make sense, because if the potential differences are the same, then there's no difference between the battery and the capacitor, and there's no reason for the current to flow anymore. And so that's when we say that the capacitor is fully charged. All right, so this is kind of some of the basics that you're going to need. Now, a couple other things that I want to mention. What happens when capacitors are in series? We talked about this for resistors, and remember, when resistors are in series, we just add up that resistance because the current has to go through both of them. Now, if you look at your formula packet, the formula packet actually shows you what happens for capacitors in series. And what you'll notice is that it's actually the opposite of what's true for a resistor. Now, this should kind of make sense. Recognize that if you have two capacitors here, what that means is that the potential difference across the cell is going to be the same eventually as the potential difference across both of the capacitors, which means, for example, if the cell has a potential difference of 4 volts and these two capacitors are the same, then each of those capacitors will only have a potential difference of 2 volts, right? Because I only have 4 total volts. And so as I go across one, it'll drop by 2. As I go across the next, it'll drop by 2 as well. Kind of like as we go through a battery. But they have to add up to the same thing as that 4 volts. I can't have more potential up in the capacitors than I actually have in the battery. And so therefore, each capacitor is now going to have less potential. Now, if it has less potential, let's go back up to this formula up here. If there's less potential up here, then that means that there's going to be less charge stored on each of those capacitors. And it should kind of make sense that if there's less charge, then there is less effective ability of those capacitors to store energy. Now, we'll look at energy here shortly in just a minute. But for now, I want you to recognize that that means that those capacitors are actually going to do less than what they did when they were by themselves. Okay? And this leads us to the formula, which is in the formula packet, similar to the resistors in parallel, that the capacitance, 1 over the capacitance in series, is going to equal the sum of 1 over each of those capacitors added up, okay, from I to however many there are. Now, of course, the question that follows is, well, what if they are in parallel? Okay, well, let's see. So we put it in parallel. There we go. Now, remember that the potential difference, whatever we have here, has to be the same as the potential difference across the capacitors once they're fully charged. Now, notice that, for example, if this was 5 and this was 0, then all of this would be 5. All would have to be 5. Remember that the potential difference doesn't split, and all of this would have to be 0, which means that each capacitor still has the same potential difference as the cell did. Now, what that means is that, looking back up to our equation up there, the potential difference equals the charge over the capacitance, that if it has the same potential difference, it's going to end up having exactly the same charge as it did before. So therefore, I now have more capacitance than before because they're in parallel, because they can both store exactly the same amount of charge as before, and so now I'm able to store up exactly twice as much charge as I started with. All right, and this leads us to that second equation, which is in your formula packet, which is that the capacitance when in parallel is just equal to the sum of the capacitances. Now, one last thing before we move on, I do want to talk about energy just for a minute here. All right, now this may be a little bit challenging, but they do give us the formula in the formula packet. The energy in a capacitor is 1/2 Q delta V. Okay, now you might say, well, I thought that, we learned in our cycle that energy divided by charge was potential, which means potential times charge should be energy. So you may be wondering what this little 1/2 is doing here. Well, the U divided by Q equals V works when those things are constant. In this situation, remember that the capacitor starts with no potential difference and builds up to have the full potential difference that it can hold based off of whatever the circuit looks like. Now, because of that, the potential energy that ends up being stored is half of what it would be if it was just Q times V. All right, so it's not the full amount because the energy is not the same. We don't have to work against that same potential difference all the time, Remember, initially, it's really easy to get the charge there and takes relatively no work, but then as the capacitor builds up and as the potential builds up, it gets harder and harder to move those electrons there, which then builds up more and more energy. And so therefore, the answer is the average. We get the average of the energy. And this is exactly what's in your formula packet. So don't worry about it too much because it is in your formula packet, but please do remember that when finding the energy of a capacitor, you need to use this formula, or when finding the amount of work that it takes to charge up a capacitor, those types of things, you're going to want to use this formula. Okay, now you should be able to, we're not going to take time to do this now, but if you want, you can go ahead and prove on your own that this is equal to C delta V squared, which if you look at the equation up at the top, the delta V equals Q over C, it should be somewhat self-evident there. I should make sure to mention, just so that you remember, or in case we haven't talked about it or you haven't seen it before, the units for capacitance are farads. Okay, now 1 farad you can probably figure out from the equation up there for the potential equals charge over C, is that 1 farad is exactly the same as 1 coulomb over 1 volt. All right, so it's in SI units. Now, this is actually a very, very large amount of capacitance. Most of the time, you're going to be seeing microfarads, nanofarads, possibly even millifarads, right? But anyway, you're going to be seeing very small things. We do that just because we do want to keep it in SI units, and 1F is equal to 1 coulomb over 1 volt. Now, you may see it in different units than this. Obviously, you can rewrite the volts in other types of units. You can break it down into fundamental units if you want. The coulombs can be turned into the amperes second, right? So you can do a lot of different things with the units, but that's the basic idea, and it is SI. All right, now, as we go on to the next couple of videos, I'm going to show you a couple of examples of how we can deal with capacitors, both finding the total capacitance of a circuit and also just kind of dealing with what happens when we combine them with other things. All right, so here we go.